The history of math is our intellectual foundation to understanding science. Science. Beautiful, awesome, wonderful science. It's the creative foundation to our ineffable future. Hi, I'm Gabrielle Burchak, and this is my podcast, Math, Science, History. I often promote my website, mathsciencehistory.com, which I built myself. Of all the hosts that I've been with, my experience with Bluehost has been the best. What I really like about Bluehost is their customer service. It is top-notch, and they are always there to help me. So if you're looking to build a website or you're looking to move to a new host, I highly recommend Bluehost. You can access Bluehost through my affiliate link, which is www.bluehost.com/track, TRACK/mathsciencehistory, all one word. Bluehost is fantastic, and they are affordable. It's only $3.95 a month if you sign up for 36 months. So if you do the math, it's $142 to start. And for me, it was the smartest business investment I've ever made. I'm going to start my podcast with a digression because today I read some very exciting news. The National Science Foundation has awarded the University of California, Berkeley, $25 million to create a multi-university institute that will advance quantum science to create quantum computers. This excites me because it's going to take math to a whole new level and make it powerful beyond numbers and words. Though quantum computing is young, the opportunities that it presents are truly mind-blowing. Unlike the conventional computers that we use today, where information is stored as bits, quantum computers store information and data as qubits, also known as quantum bits. You see, the computer that you use today is streaming electrical pulses that represent ones or zeros. Though quantum computers also use zeros and ones, they also use superposition and entanglement to create a third state of qubits that represent a zero and a one simultaneously. We don't have quantum computers for public use yet because we're still executing computational operations on a small number of qubits. Furthermore, these processes require a computer to operate at negative 460 degrees Fahrenheit, also known as negative 273 degrees Celsius, also known as 0 Kelvin. Quantum computers are going to be the future of computing. Used today, they can solve problems that would take a conventional computer billions of years to solve because they are thousands of times faster. Because of their power, they'll be able to break encryptions. However, also because of their power, they will be able to create unhackable systems. Also, instead of using electricity like our conventional computers do, quantum computers will use quantum tunneling for power. As a result, quantum computers will reduce the consumption of power that a computer generates. But to me, the most exciting thing that a quantum computer can do is find a product representation for the solution of Pell's equation in polynomial time. To simplify that statement, polynomial time is the time it takes to do a computation depending on the amount of inputted data. That is actually irrelevant to this podcast, but it's good to know for interesting party conversation. What is relevant is that a quantum computer can find a product representation for the solution of Pell's equation. You see, Pell's equation, also known as the Pell-Fermat equation, is any Diophantine equation of the form x squared minus ny squared equals 1, where the variable n represents a positive non-square integer. In this equation, solutions are solved for x and y. I'll post the equation on my website so that you actually have a visual of what the equation looks like. But when the equation is presented in Cartesian coordinates and n is positive, it's also shown as a hyperbola. And when n is negative, it's an ellipse. I'll show that also on my website at mathsciencehistory.com. This particular equation, according to Joseph Lagrange, has infinite integer solutions as long as the variable n is not a perfect square and x and y are integers. Though Diophantine equations have been around since the mathematician Diophantus presented his work called Arithmetica around 250 CE, it wasn't until 628 when Brahmagupta Brahmagupta discovered an integer solution to this equation when n equals 92. Brahmagupta was a tremendous mathematician. The world-renowned science historian George Sarton stated that Brahmagupta was, quote, one of the greatest scientists of his race and the greatest of all time, unquote. Brahmagupta was born in 598 CE in India. In 628, he wrote and improved the treatise of Brahma called Brahmagupta. The book consists of 24 chapters and has 1,008 verses. It includes astronomy, algebra, geometry, trigonometry, and algorithmics. The solution to the referenced Diophantine equation is found in Chapter 8 of Brahmagupta. Though it seems like a simple process today, he was solving for large numbers using Diophantus's process of syncopated algebra, which was the process of using simple symbolism before it evolved into symbolic algebra. As a result, in Brahmagupta's time, he only had symbols that represented exponents, subtraction, and an equal sign. That was it. Symbolic algebra wouldn't be used until the 16th century. The contribution of Brahmagupta's work to mathematics is extensive. For example, in arithmetic, we have the four fundamental operations, which are addition, subtraction, multiplication, and division. Even though these fundamental operations had been around for centuries, the current system that we know of is based on the Hindu-Arabic number system, and it appeared in Brahmagupta. And speaking of zeros and ones, Brahmagupta was the first existing book that treated zero as a number and not just a placeholder. Prior to this, in Ptolemaic mathematics, zero was used only as a placeholder. However, though Brahmagupta is contributed for treating zero as a number, in 2017, research uncovered an Indian manuscript that dates as far back as 200 CE, and it shows the use of zero as a number. So, regardless, we would not have been introduced to this concept of zero as a number if it wasn't for the work that Brahmagupta presented in Brahmagupta. I'm going to post a video on my website at mathsciencehistory.com, and it's from the University of Oxford, and it shows the research that uncovered the Bakshali manuscript. And it's really cool and it's exciting because now we're understanding that zero was actually used as a number further back, closer to 200 CE in India at the same time that the Romans were using zero as a placeholder. Brahmagupta was also one of the first to provide rules for multiplying negative numbers. All of this played into several rules that showed that the sum of two positives are positive. 1 plus 1 equals 2. The sum of two negatives are negative. Negative 1 plus negative 1 equals negative 2. The sum of a positive and a negative is the difference. Negative 1 plus 3 is 2. And if the sum of a positive and a negative are equal, the answer is 0. Negative 3 plus 3 equals 0. Brahmagupta also described the process of zero and negative numbers in multiplication. He showed that the product of a negative and a positive is negative. The product of two negatives is a positive. The product of two positives is positive. And he also showed that the product of 0 and a negative is 0. And the product of a positive and 0 is also 0. As far as triangles go, for the sides of the right-angled triangle, he presented two sets of the Pythagorean triples. In geometry, he created an exact formula for finding the area of cyclic quadrilaterals. A cyclic quadrilateral is a quadrilateral that is inscribed within a circle where all the vertices sit on the single circle. I'll post that formula and the process for finding the area on my website as well. His work with cyclic quadrilaterals led to Brahmagupta's famous theorem, which stated that if a cyclic quadrilateral has perpendicular diagonals, then the perpendicular to a side from a point of intersection of the diagonals bisects the opposite side. There's actually a really great image that goes with this, and I'll show that and the mathematics that go with it as well. So he was phenomenal. He contributed so much. In astronomy, though he believed that the sun orbited the Earth, he presented an argument for showing that the moon is closer to the Earth than the sun. The evolution of mathematics is such a beautiful one. Brahmagupta's work helped to speed up the calculation process of the Diophantine equation. Today, we begin to move forward into a new chapter of quantum computing as the process of crunching large numbers and data becomes faster and easier. And though we have many problems to correct, including noise and error correction, and though we may not see quantum computers for a while, and though it is highly likely that quantum computers may not outpace or even replace conventional computers, initially, we are stepping into a new chapter where even our fastest computers today will become antiquated. With this progress, the numbers that we understand today may change by definition and representation. As a result, as mathematicians and scientists, we stand at a place in time that serves as a marker for the future of mathematics. Yeah, we stand along a linear path, specifically at that point between history and the future, where we can see all that brought us here mathematically and all that will take us to greater understandings. I know it sounds a bit dramatic and poetic, but it also sounds really exciting. Thank you for joining me at Math Science History. If you enjoy this podcast, please subscribe to the show. If you could also please leave me a rating or a review, I would love that. If you want to learn more about the history of math and science, please visit me at mathsciencehistory.com. And if you like what you're listening to, please feel free to click on that coffee button and buy me a cup of coffee. Every cup of coffee that you buy helps me keep this podcast up and running. Also, if you're interested in leaving me a comment or chatting with me, you can always find me on Twitter, Facebook, Instagram, and Goodreads. Just search for Gabrielle Burchak. Thanks for listening. Until next week, carpe diem.